Wow, I'll let you guys have more time. So we'll go for 12:15. Can I have 12:30? All right, we'll try 12:15. Subtraction, MVPA, RSA, encoding models. So in one sentence, I couldn't find a shorter version of this. So I define it as the model is a description of how experimental attributes relate to the responses. Maybe more straightforwardly, you can think of it as prediction. So you can predict the activity level based on whatever's happening in your experiment. So if we like that definition, you might be thinking, isn't that exactly what a bread and butter fMRI GLM does? So face predictor, house predictor, if you fit the model, then it in some sense predicts the response. Or you have you can fit data and then of course you can ask it to generalize to new data, and the prediction is whatever the beta weight is, right? So I think yes, but that's kind of a trivial encoding model. The key is you need to make a real prediction, like something that's like more general than faces and houses, like chairs. Like if you have an encoding model that is describing the attributes of having a face on the screen or having a house on the screen, how that relates to the activity in your favorite region, it should at least make some sort of generalization to some other type of stimulus. Or at least this is the way I think about it. So yes, technically it is an encoding model, but it's kind of a trivial one. Okay, so here's me on my soapbox about model building, at least in the definition. There are many senses of the word model here. I described encoding model. I think it's a very natural thing to do, and I'm curious why we don't do it more. So here's my little cartoon. There's can you move that little box? There's a little article I wrote, kind of a philosophical or opinion article. And so 99% of all the experiments we do conform to this description. We stick one subject in, typically, in MEG or fMRI or whatever, and we have usually a visual delivery device. Even if you're interested in memory or attention or cognitive stuff, it's usually a visual thing. And so you stick them there and you ask them to do something. For vision people, it's almost 100% of the time, fixate please, and maybe make a judgment, right? So, and there's behavior often. Some people ignore behavior, but I'm happy to ask the subject to make some button presses. And then we get all this data, from MEG or fMRI or whatever. And, as a scientist, this is a complex system. There's like a complex spatial temporal stimulus. There's like a finger moving. And then there's all this complexity inside the brain happening. Then what do we do as scientists? Well, we observe and we explain, right? I observe increased activity in this part of the brain to this stimulus for some reason. So why does that happen? And so we can go off and come up with putative explanations of this, right? And we can give simple explanations like, oh, there was some spatial temporal contrast on the screen. Like there's a stimulus, there wasn't a gray screen, so that's why the activity went up. And then we can get increasingly more sophisticated in the type of explanation or description of this system. So that's kind of my setup here. And again, 99% of the experiments we run conform to this general setup, I would argue. Right, so I kind of viewed this endeavor. What just happened here was we linked experimental attributes to recorded activity. In this case, like bold activity, but it can be whatever measure. And I would say, well, trying to do this is like building encoding models, and it's a very natural thing to want to do. And why are models important? They summarize complex data. They explain why the data are occurring. You can think of this as prediction. If you really pin down the model and it's quantitative, it says, if you really believe in your model, you bring the subject back in and do a different manipulation or even the same manipulation, it says it should occur again. Like you will get this level of activity if your model is actually a good one. Right, so these are kind of prototypical functions of why try to formulate models of something, a system. And let's give a anti-shout out to word models. So word models are models, and they make some sort of prediction, but often they are qualitative. Like, we expect increased activity, but it doesn't really make a quantitative statement of how much increased activity. So if you have a quantitative model, then you can for sure falsify it. But if it's some hand-wavy, abstruse word description, then you can always play games about, oh yeah, that's because this and that, but that's just hand-waving. Okay, so overview of how to do modeling. Don't read this box, I'll just kind of walk you through it's very, I think, straightforward. So typically we want to get a rich set of data because we want to explain variance. Like, you want to show many stimuli to kind of prove that your model makes really good predictions under a lot of conditions. So you kind of have to choose in the end what type of stimuli or conditions to sample. So that's a hard choice. Then you go get your data, and then you're faced with all this data. So beta weights or time series or whatever, and you're gonna have to come up with some proposal for what it is about the experiment related to the activity, right? So you have to pick a model, or maybe you had a model in mind, or you're gonna think about it and you're gonna brainstorm. And so you pick a model, it's gonna have parameters, so then you're going to fit those parameters to observe data. Typically you have free parameters, like the tuning width, or the preferred stimulus, or what have you. So you fit those model to the observed data, you learn the parameters, and then typically we do some post-hoc things like look at the parameters, and you have many voxels, many neurons, different areas, and you see like, oh wow, these parameters are changing, and so this actually tells me something about the differences across different brain areas, so you can do that. Another thing we like to do is quantify how good the model is, and that's just how well does it match the data. And typically you say predict the data because you want to leave out some data because the same old issues of overfitting. Like, you can always fit a given set of data, but does it actually generalize well to left out data? So we typically do that. And then ideally you would compare your model to some other model to kind of, you can always explain some amount of variance. So how good is that? Is it significantly better than some baseline model, or is there some other model out there that does better, and so on, right? So this is the general process that you might do when you're trying to do this approach. Of course, that's not as detailed. That doesn't go all the way to the algorithmic level or even the code level, but we're digging deeper. Uh-oh. Okay, so let's stay at the kind of conceptual level. I'll just give you a schematic diagram, and then I'm gonna, after this, give you an actual data set to give you even more, it'll feel more real if you see real data, I think. But this is just a cartoon, right? So this is just mimicking the steps we just went over. So we designed this experiment, some little trivial stimuli. All right, we go get our data. In this case, we have five different stimulus conditions, and we're just looking at one voxel or one neuron, right? And we see activity, and then I stare at this, I'm like, it seems to like stimulus 3, 4, and 5. Why is that the case? So we can sit here and theorize about this. It turns out this was a real data generated from this very simple model. So this gets at like PRF ideas, which we'll talk about in a second. But basically, it's just the, how closely does this white square or rectangle overlap the right-hand side of the image? That's all. And it's a dot product. The details don't matter. So it's some simple hypothesis or description of what this thing might be doing. Great, so that's our model. So we have to fit it. So there's some parameters. So we like do some statistical fitting. Let's not worry about that at the moment. And this is the fit. And then we can get our parameters. Remember, we're gonna look at these parameters now, not just for this one voxel, but we might look at all the other voxels in different regions, different subjects, and we might find some differences across regions. That's cool. Might look at other subjects. Okay, what else can we do? Well, this was the accuracy bit, right? Typically, we want to leave out some data or choose some new stimuli. So we actually collected 100 stimuli. We're going to leave out some of these stimuli, and we'll see, well, if this model is actually a good model, it should predict train test, right? That terminology. This is the prediction. So it wasn't fit to this data, but it was fit to these data. And then we just use that. If this model is actually accurate, it should give pretty good predictions for what the response was for the left out stimuli. Okay, that's good. So what other things can we do? This is kind of an advanced thing, but like this, you may hear the term noise ceiling. Like, your model's not going to do 100%. So how good is good? There's always noise in the data. How do we like compensate for that? So there's some issues there. This model looks pretty good. It's basically within the error. And if you interpret these as standard errors across trials or something. Another thing we can do is, and this was actually at the beginning, it kind of goes full circle. Well, let's say you do all this work and you get all the data and you realize, whoops, I didn't use the right stimuli. I actually need to sample this one condition. So you might want to go back and change this experimental design. And then one last thing we can do is, I mean, this was just, this was the real model, or the model that I simulated this data from. But with real data, you probably don't know the model, and you might try one and it kind of works, and then you have a brilliant idea and you go back and change it, and then you can do this whole process again, right? So this was just a cartoon of the previous kind of text box. Okay, so, the example we just saw was like this kind of simplistic low-level, although some people like low-level vision. But you can repeat this for whatever type of description of experimental attributes you want. So it can be some like really high-level emotional description of a movie, or semantic content, or some it could be whatever. And people have used it in various guises in the literature. Okay, so great, breakout time. We'll spend 3 minutes, Lee's group. Let's go. Comment, question, gripe?
One question there was, so I think maybe in what you were saying when you talked about initially creating the model, selecting the model, right? You are selecting the model based on the experiment, not the data. The experiment simulates what informs the model.
I guess, well, it's like the chicken and egg. Like, if you think you have a good model, you're probably going to get data that may be good to show that the model is good, right? Another approach is take the NSD data and then figure out the model, right? That was already decided for you. Now your job is to figure out the model. Yeah, so there's some like meta science issues there. Yeah, that's interesting. Next group.
Follow up on this. So I understand having a generative model that has a particular goal as an encoding model, right? So you generate data from what we expect the brain to behave at certain levels, right? But it doesn't mean that, for instance, so I guess it's how a priori your model should be here.
How what?
A priori. So here you're trying to build an encoding model based on the data, right? But how do you know you're not just overfitting instead of just, a good thing about generative models is that it gives you like clear predictions of what's going to happen at some point. And at that level, like, how you validate a model is a difficult question, but I'm not just trying to predict the data, right? I'm making a statement about what I think happens at a certain computational level.
Right? Yeah. Wouldn't you just try other stimuli and confirm that it's a general description that works no matter what you put in?
Yeah, I understand how I proceed from that kind of model. What I don't understand is this framework here.
Sorry.
I think I'm having a hard time understanding how you go about that part.
Sorry, which bit was, so this was an attempt to schematize what one might do in a given study.
So you have the data from the study, and then you try to create a model for the data from the study.
Right.
The way I thought, and I'm very ignorant here when it comes to encoding models. So the way that I thought encoding models work is that you already have it before even the study begins.
Not necessarily, but
about what you expect to happen at a certain level.
Well, this is the same. Yeah, it's not. It depends on how you do science. Like the NSD data has already been collected and it exists now. I didn't have any specific model I wanted to try on it yet, but maybe now I want to spend the next week figuring one out. So that happens after the data collection. But you could have done it.
What are you trying to do?
So it's not predict in the strong sense, I guess. So rather you could see, the endeavor isn't really to predict here. It's to figure out what the representation of the brain is, right? That's not a prediction. That's a.
I disagree a little bit. You didn't have an explicit model in mind, but you had a model space in mind. For example, your data set doesn't include auditory stimuli, right? It doesn't include certain types. So there's already, you have to have a model space at least in mind before you design an experiment. Right?
Certainly. Yeah, I guess this is contingent on what's the definition of model. So, I mean, that's a weak definition of model. Like, yeah, I'm interested in visual stimuli. I think images are going to drive a lot of neural activity. I think these are complex, rich images that will probably drive a lot of brain areas. I will control the memory task part of it. Yeah, there's a lot of things we bring to the table when we got this data. Yeah, so yeah, I think it's all, I mean, these are good issues. I'm not sure, is there some fundamental problem or limitation here that you're getting at?
No, I think in my head, these are very different things, that's all. So when you mentioned about encoding model, for me, that was something that you already have a computational model in mind, and that's what you're trying to generate hypotheses from. And I think what you're doing here is getting the data and trying to generate hypotheses of all what possible models might be.
I see.
Right.
Yeah, I think you could proceed either way. I guess this was more the second way.
Right. So for me, these are.
But again, sometimes I do it the first way. So I mean, I had a face and word paper a few years ago where, I mean, these are very controlled stimuli, and I did have something in mind. That's why I did those specific stimuli. NSD is the other flavor. It's like use natural images from Coco. So yeah, one might choose one approach or the other approach, or you might do one and then two and then go back to one. Any other thoughts?
I think for this, it's still like we have the hypothesis and then we choose the model here. But because maybe it's a special case, because we study the vision and the vision field that the right and top mapping, and we actually like roughly the 1 point correspond one box on one vertex corresponding one visual field there. It's there. Then I think this is your hypothesis. The one vertices of one also corresponding to part of the visual field. Then you will build a model to predict, and you just don't know like what exactly the parameters are, but roughly it's probably the Gaussian or something. Then you will use the data to confirm what the parameters are. So for this one, I think you still have the hypothesis at first, and then use the model, and then just to confirm the parameter for the model. And then also I think encoding I think it's quite tricky than the decoding, and especially as far as I know, like now probably only have some more on the primary visual cortex. I think the relationship of the encoding is more clear on the primary visual cortex. As quite complicated in the maybe higher level visual area, people still don't know like what exactly the model happening in the higher level. And we need more work on that. Then when you want to build some model on that part, you need have more hypotheses, and then you build a model according to your hypothesis. I think that's how this works.
Yeah, I think what you guys are touching on is there's flexibility in exactly how you go about this. This was just one path through the forest. Yeah, and so yeah, if you have a PRF model that you're happy with and you're more interested in the parameters, then you can use experiments and modeling for that type of derivation. Whereas if you want to go model hunting, that's like a different type of study. So yeah, I think it's all good, different ways to approach the situation. Okay, moving on. Something I already talked about, PRF. So what is that? It really just is a special case of encoding models. So let's define these terms. It really is the case of applying encoding models to largely early areas, but it does kind of apply to later areas where the relevant attribute you're proposing is just visual space. So on the left, the right, above, below, fovea, periphery, that type of thing. So remember our definition of model, it's a description of how experimental attributes relate to the observed neural activity. In this case, the attribute is space, visual field. right? So if you're happy with that definition, let's just review. Receptive field, at least in the case of vision, is like a window into the world. So it's a region of the visual field like this little hypothetical receptive field, and you're measuring from some neuron traditionally, and you're like, it doesn't respond. And then all of a sudden it starts spiking when there's visual contrast happening in this little window onto the world, right? And so that's the idea of the receptive field, and population receptive field is just emphasizing that in any neuroimaging technique, we're not measuring one neuron. We measure the aggregate response from our voxel or electrode. All right, so if you like these definitions, fine, that's what PRF is. And of course, there's a whole slew of interesting issues that arise, like how does the organization of these receptive fields change across areas or within an area, and so on. So, at least in my view, PRF is a special case of an encoding model. And now I'm going to turn to our real world example of doing encoding model stuff. And it turns out this example is a PRF model, a spatial model, right? So this is the face cortex now, so not low level necessarily. So this was the experiment we did. And so this is a movie of the experiment. There's this little fixation grid. We did include some control stimuli, but for the most part, these were complex high-level images, but tightly controlled for position and size. So visual field type stuff. So on the right, on the above, below, left. So going back to fMRI stuff, I mean, this is like a rapid event. People have different thoughts. Some people call this like a mini block design. I mean, these are 1, 2, 3, 4, 5, 6, 7, 8, or 7. I think I counted wrong. Anyway, 7 faces, about half a second each. So it's about a 4-second trial, and then you go on to the next trial. So whether you want to call that event or block, I don't really care, but they're relatively brief. And you just do this, and your job is to just fixate. And so it's stimulating, and sometimes it's right in the fovea, sometimes it's in the periphery. We actually manipulated the task in the study, but let's just ignore that. So just a summary of the experiment. I had some prior a priori expectations, so I chose this particular grid to use. I use faces of 3 different sizes. I had some hope that this would generate a nice data set. So then we went off and did some fMRI, low field or moderate field, moderate resolution. Remember all this business about cortical surfaces. We zoomed in on face selective regions using separate data, pretty standard in the field, and we defined these regions and we selected these voxels because we thought that's interesting cortex to focus on. So we did all this kind of prep work. So remember that fMRI is behind here. But then we're going to turn our hat now to the modeling process. So we already had some sort of model in mind. I guess this came from a previous study. So this was a case of you kind of do some tweaking and thinking and developing, and you get a model from this previous study, and then you take it to the next level and like test it or see how well it generalizes. So the model, I'll now walk you a little bit through the math, although it's basically like what you just saw. So remember, we're trying to link the experimental attributes to the response. So what about this stimulus is related to the response according to this model? Well, it's essentially its spatial footprint on the world, the part of the screen or the visual world that it occupies. So that's a big presumption. So it could fail horribly, we don't know. So you represent the stimulus like this, and then you essentially apply this little PRF Gaussian thing. So what that means is this is an image, you take the dot product of this image with this Gaussian set of weights, it's a weighted sum, same old linear algebra stuff. The dot product of that and that is very high, as you can see, so it'll be a high result. There's another part of this, which is a nonlinearity. I don't want to get into too much, and it's critical. So this is transforming that result of that dot product according to a compressive function. And then that's the proposal for what is the observed activity from this one stimulus in some putative brain area, like some of those face selective regions, right? Almost trivial model. There's nothing that deep here, but that might be a good thing, depending on your point of view. Okay, so that is the proposed model. I'll skip the breakout. And let's look at how that worked for one voxel. Right, so we're picking from a region called IOG. It means inferior occipital gyrus. Inferior occipital gyrus. Remember your anatomy in the left hemisphere. So we're in the left hemisphere. You might expect some contralateral responses. In fact, that's what we see. So this is just visualization. We measure, I think this is for the small face size at different visual field positions. You're always fixating the center. They extend out 3 degrees, so it's about 1, 2, 3. So faces are roughly in the central visual field, and the color just means % bold, right? We did pre-processing, we got the time series, we did the GLM analysis, we have amplitude of bold response to every single condition, and now we're just looking at the data. And lo and behold, it tends to be red in the right visual field. So that's contralateral to where this voxel lives. So that seems sensible. Let's just look at the data again in a different format so we can put some error bars on the data points. So I'm just showing you the data points going across and then down. So the first row is up here, so it's basically nothing. I can show you the second row, pretty meager. Third is starts to show something, 4, 5, 6. Whoops. So that's 49 data points with error bars. % bold is a y-axis. Clearly this voxel loves these stimuli. So why is that? So the model proposes it's really just the spatial extent of these little face stimuli on the screen. So we can take that little quantitative model, fit it to the data, but sorry, I'm jumping ahead. We also got, oh, sorry. We did fit it, but I'm kind of holding the nugget here. Fine. So this was the small face size, and I can show you a model fitted to this one voxel, and it's fit. It looks like this, and it also looks like this if you want to visualize it like an image. So you can say, you know, it's basically capturing what probably is the signal. Of course, we can look more quantitatively. Is it actually fitting the data quite well? It looks pretty good. It also turned out, this was the thing I'm missing, and I'll just move on. We also got data for medium-sized faces and actually fairly large faces, positioned at the exact same positions. The center of the faces were shared the same centers as the small faces. And so here's the full set of data. So now there's 49 times 3 data points, a lot of data points. But with, you know, the good visualizations, we can kind of make a sense of this at a large scale. And lo and behold, it fits this large set of data quite well. And I will just mention the static nonlinearity, that compressive thing, is actually really important to do this well. Anyway, so that's what happened for this one voxel. And we can furthermore quantify what was the actual center of the Gaussian in the model and its spread and things like that. So those are the parameters that we learned by fitting the data. Right, so pretty straightforward. Data and model look amazing. Okay, so then we can go off and do other quantifications. I'll just show you one slide because the point of this is not really the visual aspect, but the methods behind it. But once we do this fitting process, we can start visualizing, as is pretty typical, different voxels in V1, their centers, their spread. We can look at other regions of interest like V4 and these face selective regions. So the top row is pretty straightforward. It's just looking at many Gaussians, but on one figure. So it's like this little coverage map. The bottom one, I'll just mention briefly, it's just a fractional measure. So it's for each point in this part of the visual field, what fraction of the voxels in this one region cover that point. So it's really like summing a bunch of these circles together. And as you can see, V1 has very disparate receptive fields, different voxels, different neurons represent different parts of the visual field. Whereas once you reach FFA, which, sorry, this is posterior fusiform gyrus, this is mid fusiform. Collectively, this is termed FFA or fusiform face area. You can see that here it's a very different situation. So it gives you some insight as to the transformation of the representation of the visual image across these different visual areas. So that was a real world example. And so let me summarize. I think of encoding model as the following. It's a formally relating experimental attributes to the observed level of response in whatever you're measuring. In this case, fMRI bold responses. And I would say this is very natural. Nothing weird is happening here. And PRF specifically, if that's something you're interested in, it's just really a subset of this larger approach. And finally, going back kind of to the subtraction and MVPA stuff, thinking about univariate versus multivariate, at least the way that I described it here, it's a very univariate approach. Like when you do regression, you have like one Y that you're trying to predict. That's, in this case, we had one voxels data set that we were trying to fit well. But I will mention, you can do this multivariately, and CCA, canonical correlations analysis, is like the first thing that comes to mind if you want to model kind of a many-to-many relationship. So it is possible in a statistical sense to do something like an encoding model, but have it multivariate in nature. Is very non-common, but I just want to mention that it's possible. Break time. Yeah, we have time. Mongoose. Isn't that you guys in the back? The mongoose?
Oh. We were talking about a few things, but I guess one of the things that I guess I've been trying to struggle to so in the area that I work on, there's very few explicit quantitative predictions, I guess. So I work in sentence processing, and we have very few models that make these kinds of concrete predictions. So I've been trying to come up with what the equivalent of something like this would be, and struggling.
Yeah, no, I mean, that's good, or it's hard.
Yeah.
Yeah, I mean, that's a common, you might even say, criticism of like, oh yeah, you could do this for like easy brain areas.
In some cases, like word probability and stuff, that those, I think, those kind of quantitative predictions are really difficult.
Cool. This group, do you guys have a name? I forget.
We were talking about two different things. First, we're just looking at how what the bold response is depending on the phase size, and so what exactly it's feeling, because it seemed that if you go to the large phase response, it seems that the bold response is higher on the edges rather than the center, which I get. It's probably it doesn't mean that. No, on the data matrix. There, yes.
Oh.
So yeah, which at the same time, when it has a smaller phase, which is the first matrix, it could just mean that it is a smaller phase. We could be showing a similar, I guess, behavior in like the bold response, what exactly it responds to. And then in general, we were wondering about again, how you know that, okay, we're fitting the data, but
so it's just the importance of quantifying your model and seeing exactly how well it fits your data, because you're taking a model that you've decided on and you're trying to make sure it, like, try to see how far it matches with the data that you've collected. And just, it's always important to go back and make sure that there is, like, that you can quantitatively explain the similarity.
Yep. Yeah. So I guess what I showed here was not cross-validated. This was just, I think I generated this figure just from a pure fit all the data. But yeah, certainly you can leave out data and check, or repeat the experiment and do a pure prediction, like do a whole new session and actually write down the prediction before you even collect the data, like that. Almost no one does that, but that's an ideal to strive for. Cool. Any other comments?
So we're just wondering, what's the difference between an encoding model and a GLM model if you only have fewer regresses? So your encoding model is just a simple regression model.
Yeah. I guess my view is, yeah, it's a trivial encoding model, but.
So like, if your encoding only applies if you have a lot of.
Well, it's not just having a lot of conditions. Like you could run 20 different conditions and have a 20 predictor GLM, but it doesn't describe the experimental attributes. Like the attribute is just a dummy variable. It's like or at least, let me scratch that. The way to think about it is let's say you run a 21st condition that's unlike anything you've ever measured before. Your 20 predictor GLM can't say anything about condition number 21, right? If it doesn't match one of the 20 that you've already done. Or at least that's the way I think about it. So statistically and technically, you can churn through all the stuff in exactly the same way. It's just that you can't churn through the stuff for the 21st case because you have no conception of the attributes of the 21st thing. Like, you have to like appeal to something like, oh, it's actually the emotional content of the 20, and then maybe you can measure that emotional content of 21, and then you have predictions. Then you can actually churn through the technical stuff.
So is this distinction then that you're making just because the GLM is generally done in the context of like a ANOVA or something where you have
right
binary
right dummy coding things like I decided these trials were A, and I'm just going to code that as A, and I decide the next ones are B. But these are just dummy codings. Whereas if you generate features, not just dummy variables, and features that come from a model or some behavioral quantification or something, then it starts having actual explanatory power and meat to it versus a dummy coding variable.
But in that sense, if I have multiple regression, right? For you, that would fit the definition of an encoding model, just because you have the features that are continuous, and I'm using that to predict a bunch of other stuff, right?
Mm-hmm. I think. Yeah, if you did, once you move away from coding trials, like labeling the trials as A, and you start going towards features, like you have 3 predictors that somehow combine to explain that data point, then I would start thinking of that as a non-trivial encoding model. Okay, moving on. We keep peeling back the onion. We haven't really talked about statistics too much. And there are some interesting issues. I'm not going to go in. I'm just going to kind of seed this in your brain. The noise ceiling we briefly talked about. That's an interesting issue. How do you actually do that? How to optimize your stimulus sampling. Let's say you do have a concrete model in mind. How best to test it. There's also how do you actually choose? How do you compare different models? How do you decide one model's better and do statistics on that? Exactly how you divvy up your data, how you prepare the cross-validation across subjects or trials or whatnot. When you fit nonlinear models, there's tricky issues of local minima, and there's also heavy computational costs depending on what type of model you choose. How do you deal with that on hundreds of thousands of voxels, and so on. So there's this little bonus lecture that we're not really going to go into. You can look at it. It's on the Dropbox or on the NSD Abu Dhabi folder. That gets into some of these technical issues. It's actually just a glossary. And the first step to figuring this all out is figuring out what all the words mean. And I'm just going to mention there are like a hodgepodge set of materials on our website. Maybe I should organize them better. Okay, I think this is my last slide. Oh, we're doing good on time. So we heard about subtraction, MVPA, RSA, encoding models. How do you like hold this all in your head at the same time? Before I get there, there are 2 basic terms you probably, I mean, we use these terms already, but we never really define them, encoding and decoding. And these are like amorphous words, but one definition is the following. Encoding is, given that the experimental conditions were like this, what do I expect the response to be? And then decoding is just the reverse. Given that I observe these responses in these voxels or regions of interest or whatever, what do I expect the experiment to be? I guess grammatically I should have said, what did I expect the experiment was or something, given that you're always analyzing data after it happened. Okay, so with those little terms in mind, fresh in our memory, our working memory, here's kind of a metaphorical way to consider these different approaches. So subtraction, I would say, is a poor man's encoding model, or poor person's encoding model. And a detail is it typically is univariate in nature. Actually, always is univariate. Okay, MVPA, what is that according to me? I kind of want to emphasize the similarity. Yeah, it's fancy and it's reversing the directionality, it's decoding based, but it's essentially doing something, the same function of subtraction. And parenthetical, it's typically done for multivariate cases, but you can think about doing it in the univariate case. Okay, what is RSA? I guess the keyword is many. So I don't think it really conforms to either encoding or decoding, but rather it's a different thing. It's a way of preparing the data or quantifying the data to help assess how the responses in a region change across many conditions. And again, typically it's a multivariate, but you can construct an RDM matrix from one voxel. I keep saying this to people. I just want someone to do it just because it's funny. Right? If you have one voxel and you measure 10 responses, you can measure the distance between all of the 10 conditions from that one voxel. You just like subtract. And then maybe take the absolute value. And then you get RDM. Okay. And then what are encoding models? Well, according to me, it's an approach that formally, so that's the key word, tries to predict response levels. And as we just heard, it's typically done univariate. That's easiest. It's very interpretable. But you can try to do this in a multivariate fashion. I'm not sure what the advantage is. And I think it has disadvantages. It makes it difficult to interpret. Okay, so we'll have, if you wanted, there's a little review article we wrote. It's a little more technical, but gets at some of these issues. And I think that's the last slide. So let's have one last breakout on this, and then we'll break for lunch.
Subtraction is a four-lines encoding model. That
The boss man has a comment.
So the thing we were talking about is about decoding models. That there seems to be a difference that we didn't really cover yet in just being able to decode some arbitrary. Well, basically, can we predict what the observer was looking at or was listening to based on just a middle response that they're measuring? And I think in the end, that's not what we want to do. We want to talk about representation. And we want to say, can we understand what a particular brain area, what the brain is representing? And it's always tempting to confuse the first one for the second one. So just because you can decode something from a population doesn't necessarily mean that you understand what that area is representing. And there's a number of papers that are out there talking about confounds, right? So there are unanticipated things that you put into your stimulus that a decoder can exploit, but has very little to do with the feature that you're actually interested in. I know about motion perception because that's the kind of work that I do. So in motion perception, if you have a stimulus that moves across the screen, it also, you can think of it as creating traces, right? So they're just shooting stars across the screen. If you now have an orientation detector, you just pick up that orientation, and it can tell you what the motion direction was presented. If you want perfectly fine, which is simply just because you're presenting an orientation signal at the same time. So V1 is very good at decoding motion, and similarly it's motion selective. But you'd be mistaken if you would say that that's where primary motion perception, or the representation of motion happens. There's a whole cascade of areas subsequent to that are required to actually put motion as an equation.
That's good, but that is this point, but that's a concrete example. So this is your motion direction, but you didn't realize that you had these weird edge things or other things that.
But that still goes through the first part, right? You can still say, well, okay, but there's different features that you can pick up on, and that's really what your decoder picks up on. But it doesn't tell you anything about how visual energy is represented or how humor is represented. That's hopefully what you're interested in. It just says that humor is a way to do the classification.
You mean this panel or this panel? So this was highlighting that it's not actually motion direction that you're representing, it's actually humor. And then you're doing a subsequent point, I think, which is you want to know how, which in your definition is like mapping this to voxels and seeing how they're tuned and things like that.
Yeah, I mean, so, I don't know, if you have more specific, right? So how do you represent humor? It might be that there's a fundamental inability for the brain to represent sarcasm different from irony or something like that. And that would, well, so you would have to do additional analysis to figure that out. And that might have something to do with the way that you are representing that information.
Mm-hmm. Other groups have comments?
So if your features are correlated, that will affect the recorded and will not affect RSA.
Yeah, no, that's an important issue, but let's clarify. Features are correlated. So RSA, so bare bones RSA means construct an RDM matrix from data. So in that process, there are no features. It's just data, right? Sorry, are we still talking about RSA? So, okay, you can construct a data RDM, like voxel-based RDM thing, and then you can construct a model-based RDM, like from some, yeah, so in this case, the model, which two models? The data in the model, or you mean features in this model? So, multiple models. Okay. So, right. So here's the data, the 2D matrix that you're trying to explain in that sense, and you have 3 potential model-based RDMs. And you're saying these two might be somewhat correlated. Yeah, that's true.
We can use encoding models to compare models and get back correlated features. So affect you over. For example, in this, if your auditory model and visual model are correlated.
Right. Yeah, so that definitely is an issue, but standard regression gives you some hope at teasing that apart, right? You can have 2 predictors in a multiple regression model that are somewhat correlated. And the whole purpose of multiple regression is figure out how much is attributable to this one versus this one, like fit the beta weights. So it should all work out, I guess, is my bottom line. But certainly it is something to be thoughtful of. Like the fact that you might observe high auditory variance accounting, great. And the fact that this is high might be a trivial result of, in your movie, it tends to be loud when there tends to be visual stuff going on when the movie is also loud. So yeah, so it's important, and maybe your point is, it's important not to overinterpret this thing. So the fact that visual features can have some explanatory power can be a very trivial consequence of the experiment you did had correlations between the features. I'm not sure RSA avoids that or in any sense, but it gets more complicated in RSA actually, I think. I haven't fully thought that through. So I don't think this is like a problem here, and it probably also is an issue in RSA, but maybe not a problem. I'd have to think about it more.
So I think this is just really what you're saying, that just because you can predict outcomes doesn't mean that you understand the process, which is the point that you're doing there. But so if I'm in a machine learning world and all I care about is making useful predictions for something, then it doesn't matter, right? All I care about is getting, I can throw everything in the kitchen sink, making my predictors as long as I get a better result. Right? Yeah. So there's some use cases for that, right? But if you're trying to understand how the brain works, that is maybe not ideal because you just, I can make useful predictions, so I have no idea how I'm actually making it. That's, I think, what the subtraction method or something where you have a coding model or something that's a little more judicious, what kind of information are you using to try to make those predictions?
Yeah, I agree. Well, yeah, I think it's a good point. Another point I make in that opinion paper is like, once your model gets exceedingly complex, you start losing on that end also. So now you have an encoding model, say, but you start losing the ability to understand what it's doing, which is like the machine learning context. So that's a little ironic, but that is a pitfall of that.
But I think it's always a tension we're going to have that a good model might not be a good model for prediction, right? But it might be a good model for understanding.
Right? Yep. I talk a little bit about that also in that paper. Some people don't like that. Some people say like, understanding is subjective, blah, blah, blah.
I mean, I say that, but it's just, that's how science is working.
Assuming this slide, let's say if your encoding model successfully account for these different features, and then after accounting for these features, you still get successful classification of this particular variable that you care about. Yeah. So So would you then can make the conclusion that these voxels encode a movie genre?
Now we got to define that word. But I would say, sure, it encodes movie. No, wait, no, would I say that? No, I guess I wouldn't say that. I would say it gives rise to discriminable genre stuff, but in those voxels, but really what they're encoding is auditory energy.
Yeah, so I guess like basically my question is, given there's in the B sort of column, there are so many possible features that can underline all sorts of classification. Like what is the goal of doing this? So let's say that I can just add so many features and then assess their contributions to this classification process.
So the question is, what is the goal of the whole experiment, or the goal of, like, what's your question?
My question is, like, if you can't say that these voxels, after accounting for these features, can or like make a conclusion that they encode a certain variable or like a certain thing or represent a certain feature or things like that, then I don't know what this model or encoding models in general can.
Wait, I'm not making that claim. I would be the optimist here and say, like, yes, you can figure out which one is the right one. Am I missing what you're?
I think it depends on the research question. What is your research question? So the research question is trying to understand what part of the brain is trying to, I don't know, represent some of the information about some categories or something. Okay, so, and then you happen to use the different movies as your simile, and then you did see the differences. And then you try to understand what actually, account for the differences and the different hypotheses would be the vector energies or something, and then do a model to try to understand the different features. So, it's very complicated, so it depends on what you want to ask, and then I think that these are just the tools that you can use.
So there might be a deeper point maybe you're getting at, which is, typically, let's stick to this example. So action movies and romantic comedies. So like, let's say you really thought genre was it, but then you're faced with these potential other explainers, confounds. Typically you would like control for these things, like equalize the volume across the movies, equalize the visual energy. That's a separate issue whether it even makes sense to, or how do you actually do that. But let's say it's impossible to. Let's say what makes an action movie is there's a lot of visual stuff going on. That becomes a deeper question. Like, what is it we're doing then?
Yeah, so I guess my sort of point example is that given this, and let's say this is true and this is the ground truth that you have to account for these features on the screen, then what can you say about these boxes?
Well, according to C, the genre model doesn't do great. It's auditory. Auditory is the winner. So you say, these are actually auditory things, neurons. They actually encode auditory stuff. And if you showed a movie that had no genre, like white noise coupled with sound, they would still respond, and they would be happy to respond, and it explains all the data.
To me, this would be going towards converging evidence. So it's not like from this individual study, you're going to find the answer that like a particular brain area is representing a particular feature. But you come into this experiment with an understanding of what visual energy is, what auditory energy is, and you do an additional experiment that either confirms or disconfirms that. I think trying to get the final answer from one experiment is probably not what you're able to do. But you can have a hypothesis about particular subgenres of action movies, and you can code it in some, or represent it in some different way. And you can specifically probe that based on the understanding that you built up in this model. I think that's the way that I look at it. And then I often like to go the other way around. So if I see a behavior where somebody's fundamentally unable to distinguish between two different stimuli that are physically different, and we can see that represented in an inability to decode based on the neural response as well, then I'm like, oh, okay, maybe now I'm onto something. I'm actually starting to track the representation.
All right, why don't we do lunch?
Yeah. So we'll be back here.
And then we'll be back at 1:30.